Okay, so part B, matter is made of atoms. If you are listening and watching at home, you should be looking at a paper that has chapter 2, atomic structure on the top left corner, 1 of 12 in the middle of the top, and this should be your first slide. Part B, matter is made of atoms. So in chapter 1, we studied the fundamentals. Now we're getting into what you guys might more commonly think of as chemistry. So the basis of chapter 2 is that electrons are arranged in energy levels around the nucleus, and the nucleus is made of protons and neutrons. Okay. Got to get used to using Mr. Hamill's. All right. Okay. So, TYSK. We'll use some acronyms in this class. TYSK. Things you should know. So this will be broken down into things that you should know. TYSK. It's like our own little texting speak. The idea of the atom and the accepted models for the way atoms behave have been shaped by evidence gathered by chemists and physicists over the last 2 centuries. This model is always changing, and it can be revised when new evidence is found. This is like a key idea to science, right? We have these ideas that we think are right, and we test, and we get evidence. And then we find out if we're right or wrong. And then someone else comes along with more evidence, and they're going to change the theory even more. We get more and more evidence. We have to change our theories, right? So I'm going to take this time to talk about Richard Feynman, one of the smartest human beings who has ever lived. Interesting character. He has an autobiography that Mr. Hamill read that he loved. I read a graphic novel based on his life. Fascinating guy who worked on the Manhattan Project. So he was one of the physicists who worked on the atomic bomb. He was awarded the Nobel Prize in 1965 for his fundamental work in quantum electrodynamics. He's one of the fathers of quantum mechanics. And really, most people consider him to be the second greatest physicist behind Einstein. He doesn't have a nice, easy to understand equation to attach to his name like Einstein does. Like E equals mc squared is just beautiful. It's beautiful in its simplicity, right? It's just, 3 letters and a number. And it's like, oh my God, that explains so much. Feynman, unfortunately, doesn't have that sort of easy to understand equation. He has these Feynman diagrams that are on the side of this van. You can see it describes in color. I think. So basically, I believe, I'm not even sure exactly how to describe the Feynman diagrams, but we're talking about quantum behaviors, subatomic level, really deep stuff that was revolutionary in the field. But he doesn't get that beautiful, easy little equation that everybody remembers. So this is my side note. If you can read about Feynman, he's a fascinating guy. His stories of the times when he was working on the Manhattan Project. I mean, talk about you have the smartest people who have ever lived all together in one room, and then they're working on, creating a bomb that can kill tens of thousands of people. So he had some regrets, I believe, later in life. So here are a couple of Feynman quotes. He's an extremely quotable man. So first quote: "It doesn't matter how beautiful your theory is. It doesn't matter how smart you are. If it doesn't agree with experiment, it's wrong." I want you guys to take a minute at your table. Talk about what you think this quote means. Go ahead, talk. At home, you can talk to yourself about it for a minute, or you can fast forward for a minute. I'll leave a little mark so that you know when to start. Okay, at your tables, chat. Okay, I am going to call on a couple of people to share their answers. I'll repeat them into the mic. Kavish, what do you think? So Kavish is trying to get me in trouble by me recording a talk about evolution versus creation science. And that's okay. His point was that as simplistic as the creation theory is, all experimental evidence holds up to evolution being the driver for. Right. It's not that either. Well, I'm going to leave it there. Let's leave it there because this is being recorded for posterity. Okay. So I like that. All right, Annie, what did you guys talk about? Yeah, no matter how much you want something to work, it doesn't matter if it doesn't work. If it doesn't agree with what you observe, right? Okay, the second awesome Feynman quote. The first principle is that you must not fool yourself, and you are the easiest person to fool. All right, talk about it at your tables again for a minute. Oh, sorry, this is the mark on the board. Quote 1. Quote 1 over. Okay, so now talk again for another minute at your tables. What does Feynman's second quote mean? Okay, guys, because we only have about half an hour, 32 minutes left. Katie, what did you guys say? Yeah, don't let your personal biases affect your work, really. Julia, what did you guys say? Okay, Julia said not to manipulate your data based on your bias. I am going to put one of our students on the mic right now so he can read what his shirt says. Kirby, what does your shirt say?
When all else fails, manipulate the data.
Yeah, that's not what you want to do. That's bad science and gets a lot of people in trouble. I think there was an instance a while back with maybe some. There have been myriad instances throughout scientific history, but one was about cloning, and I think it was in South Korea. Some people had said they cloned, I don't know, some animal, and then it turns out that nobody could repeat it. I could be wrong about what the actual science was, but I remember, there have been a lot of these cases where people seem like they have tons of data, and it's been slightly manipulated to make their theory work. Life-wise, many of you in your future will enter into lifelong relationships with someone else, and this becomes extremely, extremely important if you want to make your long-term relationship with someone work. You need to. I mean, I've been married for only 5 years, but you have to listen. I feel like I'm right a lot of the time, and I'm so often wrong. But I convince myself that I'm right. You get in these situations, you convince yourself that you're right, and you'll only look at the data that supports your theory, right? What you think. You don't look at the other data. You could have all this other data that say, like, I'm totally wrong, but you only look at the stuff that makes it seem like you're right. What's that? Chem Life lesson number 1. You'll get lots of them. Okay, so I think these are really interesting quotes and a good way to kick this off, because we're going to talk about atomic theory. So, development of atomic theory. There's actually one that predates. This is sort of like the modern history of atomic theory. The first person who really theorized, that we know of, that theorized atoms exist was actually this Greek gentleman who. What color should I use? Blue? All right. All right, blue first. Democritus. So Democritus was the first to theorize that atoms existed. He's also considered the founder of something else very important. Democracy, right? So Democritus theorized that atoms existed. And then we went about, I don't know, almost 2,000 years. Some really dark, dark years in there. Until Dalton proposed the idea of atoms. So what Dalton showed experimentally is that the conservation of matter isn't created or destroyed, but rearranged. So he theorized that their matter must be made of these. He thought that they were solid spheres. So the solid spheres were there at the beginning, and then they were there at the end. They just moved around a little bit. I forgot to point out that this is like if you want to teach scientific modeling 101, or even to like 8th graders, this is what we use, right? So Dalton proposed this idea of atoms, and he had showed experimentally that matter isn't created or destroyed. This next one, Brownian motion, is one that's not typically taught in this sort of building of the atomic model. So Brownian motion, this gentleman, Robert Brown, was looking at pollen grains. He was looking at pollen grains on a liquid, and he noticed that those pollen grains didn't stay still. That despite there being no wind current or any other seemingly outside force moving them around, that those pollen grains sort of moved randomly around the surface of his slide or of the water. So there are some awesome applets that show Brownian motion. It's actually a pretty easy thing to show because it's just, as the pinwheel goes, Brownian motion is, he didn't understand it. It tends to be random motion. So if we have the applet, if not, I have another link we can use. Oh, it wants to go so. Uh-oh. This is Mr. Hamill's. Should I accept the risk? He was the one who came up with the link. So, okay. So here's the pollen grain. If you watch here, it's just sort of randomly moving around the surface, right? At the time, there was no explanation as to why that very small pollen grain would move. So this was later explained by Einstein as this little pollen grain was getting bombarded by high velocity particles. So those high velocity particles had to come from somewhere, right? So if this pollen grain is small enough, high velocity, like random collisions with gas particles can move it around. Okay. You'll see Brownian motion a lot with super duper small particles in solution. So a lot of the work I did as an engineer was with particles on the nanoscale or even the microscale. So especially nanoparticles, when they're dissolved in solution, they move around. They can move around randomly because they're getting bombarded by, in this case, solvent particles or liquid particles. So Brownian motion is sort of this underrated part of the development of the atomic model, that atoms exist because something had to be moving the pollen grain around. So it was the collisions with these high energy gas particles, the random high energy ones that would move it around a little bit, or the high energy solvent like water particles moving it around. Does that make sense? Okay, stop. Oh, come on. All right. So now we get back here. Thomson discovers electrons. This is sort of the next big idea. So Dalton has his billiard balls. That's what they call it, the billiard ball model. He thought they were just like hard spheres of atoms. Then Thomson comes along. I'm not going to use this link, but I am going to use another one. Yes, I want to keep the ink. I'm not used to using a PC. So I put in a link under the extended study for further information on Thomson's experiment. So what Thomson did was he already knew of these things called cathode rays. So electricity was understood somewhat in the late 1800s. Nobody quite knew where it came from, but they knew if you excited atoms, you would get this beam of energy, the cathode ray. They used to use this to, like TVs used to be big cathode ray tubes. They would just deflect the beam all around to give you the picture. So what Rutherford did was he put some magnetic plates on either side of that cathode ray, and he found that he could bend the cathode ray. That meant that the cathode ray had charge. And so as he was doing the math behind this, he realized that it couldn't be that the atoms themselves were actually charged. He found the charge to mass ratio and figured out that the mass had to be way smaller than the mass of an atom. The mass had to be teeny, 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 tiny. And the charge was really, really large. So therefore, there must be a part of an atom that has what he knew to be a negative charge and very, very little mass. So what did he find? He found electrons, right? From this experiment, bending a cathode ray tube, and it's a lot more involved than that, which is why I put this up. It's 3 experiments, 1 big idea. The basics is he bent this cathode ray, found that it was attracted to a positive field, and so there must be a part of the atom that is negative, right? And that it's divisible from the rest of the atom. So that was Thomson. Okay. So we'll just say cathode ray tube experiments. I mean, that website's interesting. It gives a little more of the history behind it. If you're interested, you can check it out. So Rutherford then discovers the nucleus, which we're going to get into in the next slide. And then quantum mechanics is developed. The interesting thing is with quantum mechanics, there are no sort of simple, beautiful experiments like the cathode ray tube or what we're going to show with Rutherford. It's been a lot more of a development over the years and a lot of math, whereas this was a little bit less math. Okay, so things you should know. 2-2. The nucleus is made of protons and neutrons, which contribute most of the mass to an atom. These are things that you should probably already know. We're refreshing your memory. Protons determine the identity. Neutrons, to a chemist, are essentially dead weight, unless you are looking at decay, which we'll talk about briefly. Isotopes are atoms of the same element with different numbers of neutrons. They are more or less chemically equivalent. So different isotopes of the same element will chemically behave just about the same. Okay, so now we're getting to about the turn of last century, about 1900. So at the time, we knew that atoms themselves were electrically neutral, but that there are negative particles with a small mass. And we know that because of Rutherford. So this is what we thought an atom looked like at the time. And in all of science, I feel like this is the one name that needs to get updated. So this is called the plum pudding model. Now, be honest. Has anybody ever had plum pudding? All right, we got 1, 2. We have 2. That's the most I've ever had in a class. Not many of us know what plum pudding is. I certainly didn't before I learned of this model when I was in high school. So basically, plum pudding. Can you describe what plum pudding is like? Sort of cakey. Cakey with bits in it. Sounds delicious. Okay, that's the way I describe it now. Like, we're a lot more familiar with fruitcake than plum pudding. kind of like a fruitcake. All right, so this could be the fruitcake model. Oh, that's a good question. Is it any good? Not really. Okay. Well, neither is fruitcake. So, it's like a Christmas thing. Okay. Although I think a better way of describing this would be like the Jello with fruit model, which is also sort of strange to me. I never quite understood the allure of Jello with fruit in it. But, and I think this is a better model because what they thought at the time was that you had these negative, sorry, I need to point at the board so people at home know what I'm talking about. You had these negative electrons that were sort of interspersed within this positive goo, right? So, in theory, this was just this positive field with negative stuff inside it. Okay. Now, Rutherford came along. So he won the 1908 Nobel Prize in Chemistry. He was the first one to show that when radioactive decay happened, it actually changed one element into another. Dalton said you could never change one element to another, but it can happen if you have radioactive decay. And he's most famous for his gold foil experiment. And this was actually carried out by his graduate students. And what is this guy known for? Geiger counters, right? What do Geiger counters measure? Radiation or radioactivity in the area. Marsden sort of got left behind by history a little bit. I don't know. Mr. Hamill, was Marsden ever? Yeah, nobody sort of knows what happened to Marsden. So many of you will go to graduate school. I'm just guessing. What is graduate school like? Hopefully over the course of the year, I've been able to bring in a couple speakers in the past. When I was your age, I didn't know what graduate school was. When I was a junior in college, I didn't know what graduate school was. My advisor in college said, hey, you should go to grad school. It's fun. And I said, 5 more years of school? I wanted to get out and I wanted to get paid. Graduate students in certain fields do actually get paid. Engineers, I don't know, I think most recently, like low $20,000 per year to go to graduate school. So you get you're like right on the poverty line, but you're also going to school at the same time, so it works out okay. So it just wasn't my thing. Now I'm working on my second graduate degree, but at the time it wasn't my thing. Anyway, this is a long way of saying a lot of you will go to graduate school for sciences or engineering or med school or whatever. What you're going to find, especially in sciences and engineering, you'll have advisors who are these PhDs. And they're professors, and they're, maybe well thought of in their field. They'll come up with these ideas. You will do all the work. And who gets the credit? The professor does, right? You'll do all the work, and the professor will get all the credit. She'll take the rewards, and you'll be stuck working more hours in the lab. So Rutherford's famous for his gold foil experiment. It was actually done by his graduate student. So don't fret, though. I mean, that's sort of the way things are. Like, your name will be on the publication, so you'll get some credit. But the professors are the ones who really get the credit for the work that gets done by their graduate students. So, what was Rutherford's experiment? So, keep in mind that at the time, they thought that the atom was not much more than a Jello mold, right? So what they did is they took this very thin piece of gold foil, very thin piece of gold foil, and gold is great because it's easy to manipulate. You can manipulate, hammer it out till it's really, really thin. Not single atom thin, but, not thick at all. Hundreds to thousands of atoms. So he shot alpha particles at it. And what he expected was that the alpha particles would shoot straight through. A few might get slightly deflected, but that for the most part they'd go right through. What he found, or what Geiger and Marsden found, is that a lot of them bounced back at an angle. Many of them went straight through, right? Oh. Many of them went straight through. Right? What the graduate students did is that this detector would actually light up. So anytime an alpha particle hit the detector, it would light up, and the grad students would be like, okay, there was one here, there was one here, there was one here, there was one here. Like for days. I mean, that had to be such a thankless experiment. Not to mention the fact that they're, exposed to radiation. But anyway, so it's not, alpha particles aren't particularly harmful. But what they found was a lot of them bounced back and had some really severe angles, right? This is akin to standing in a field, holding a piece of tissue paper, getting a cannonball shot at it, and having the cannonball bounce off. That's like the way they thought about it was the same. Like they just could not understand why they bounced back at such severe angles. So I'm going to show you a little applet that sort of better explains why that happened. If it lets me. Yes, keep. So this will take a moment. You can fast forward if you're watching at home. So this site we're going to use a lot. It's called PhET. It does a lot of interactive simulations. Oh, we used it the other day with the gas particles. All right. Everybody have a good weekend. Yeah. First full week of school this week. It's gonna be, I don't know. I think it's gonna be nice to get back in the flow a little bit. Last week was like we were here for like 15 minutes, then 45 minutes, then we had the day off. 45 minutes. Okay, so I'm going to turn on the gun. So I'm shooting alpha particles now. What do you notice happening to the alpha particles, the ones that get close to the middle? They bounce away, they repel, they're repelled by the nucleus. But what do you notice? Most of them just go straight through unimpeded. But the ones that get close bounce right back. So, and sorry folks at home, I'm actually going to draw something on the board in marker. But what I'm drawing on the board in marker is what they thought at the time was that this whole field was a diffuse positive charge with negative electrons. So they would expect that most of them would shoot right through. Instead, what did they find? What part of the atom did they find? Just shout it out. The nucleus, right? So they determined that there was this really dense, small, positively charged, highly massive part to the atom. And that was the nucleus. And they found this in this very elegant experiment where they shot the alpha particles and they deflected back. You can see that some of these, the ones that get close, they bounce back at more severe angles, right? Some bounce off at higher angles. But so instead of them going through, they bounce back. A lot of them bounce back. So what does that mean for us? It means one. Oh, I haven't checked this out. This could. Awesome. The things you learn when you click on other tabs. So this is what they would have expected to happen with the plum pudding model. Explained much better than I did with my whiteboard marker. Okay? So see, they expected it just to go through like this. Okay, back to the slides.
Do it here and it'll.
Oh, awesome. Thank you. Okay. In theory. There we go. Okay, now we are back. Okay. So, your takeaways. Alpha particle. And these are helium nuclei. And we'll get to what this symbol means in a couple of slides, which may not happen until Wednesday. So, alpha particles expected to pass through the foil, gold foil. With some slight, they thought there might be some slight deflection. Instead, what they got was the cannonball bouncing off tissue paper. And their theory was that there was a small positively charged center called the nucleus. So they actually experimentally determined it. We still don't have the technology to see atoms. We're getting really close to being able to visualize atoms, like on the atomic scale. But we still can't see them. Like, no matter how great of a microscope we have, we can't, like, take a picture of it, like a perfect picture of an atom. So all this stuff is, we know through experimentation. So let's interpret the results. This is expected from plum pudding model. This significant deflection means high charge. I'm going to use this a lot when instead of writing out concentration, I just put the brackets. When we get to solutions later in the year, we'll use this all the time. But for now, scientists use a lot of shortcuts. The fact that I have to explain it now and it's taking a minute means it's actually a little longer than if I just put concentration. But over the course of the year, I'm going to use this a lot. So if ever you see the brackets, you know that means concentration. So significant deflection means that there was a high charge concentration. By measuring deflections, oh, that was ugly. Deflection allowed Rutherford, and I'll give Marsden and Geiger a little love by giving them the et al. To determine approximate size of the nucleus. So not only did they discover that there was a nucleus, they determined the approximate size of the nucleus. This is one I use a lot of analogies that don't work. This is one that I think does work really well. I use the nucleus is to an atom as a bumblebee is to the football/multi-purpose field. So imagine a bumblebee or a marble sitting at the 50-yard line of the football field or a soccer stadium or whatever you find. That marble, that tiny marble to that entire football field is what a nucleus is to an atom. Atom is almost entirely comprised of empty space. Okay. So what are our subatomic particles? Let's review. Particle, proton, where it's found, nucleus, what's its charge, plus, what's its mass? I'm not going to do it in grams. We're going to use AMUs, atomic mass units. So proton has a weight of 1 atomic mass unit. Neutrons, also in the nucleus. No charge, 1 atomic mass unit. Where are the electrons? Well, they're outside. Mr. Hamill's going to tell you exactly where in the lectures that you're going to watch online. Actually, he's not going to tell you exactly where. He's going to tell you approximately where they could be found, depending on their energy level. So, particle, electron. For now, we're just going to say outside of the nucleus. What's its charge? Negative, and its mass is approximately 0 AMU. Here's another wonderful analogy that I think actually works. So, we say the mass of an electron is approximately 0 AMU. It's not 0. Electrons have mass. If you're Bill Gates, or give me someone else who's rich, maybe not for sciencey reasons, for fun reasons. I don't like Donald Trump, though. But Oprah, all right, we're going to use Oprah. Oprah is really rich. So, if Oprah's walking down the street and Oprah picks up a dime, does that really change the amount of money she has? Not really, because Oprah's got like $1 billion, right? $1 billion plus a dime is still essentially $1 billion, right? So, the mass of an electron is like, the mass of an electron to a neutron and proton is like a dime is to Oprah. Essentially meaningless, right? Not that it's zero. That dime still is worth 10 cents. But it's not worth Oprah's time to pick it up, right? It's essentially worth nothing to Oprah. So, for us, an electron essentially has no mass. For what we care about, it's zero. Okay, let's see. Let's see if we can get through one more slide today. Maybe. Oh, there's a cool website too. I mean, I know I showed it in Chem 1. I think they showed it in physics. It's called The Powers of 10, where it takes like this couple that's having a nice, beautiful picnic in Chicago in math. Yeah, and it zooms out to like the size of the universe, telling you like 10 times bigger each way. And then it goes back in, and it zooms in 10 times down to the size of a nucleus. It's actually really neat to see, like, you know, $1,000 is a lot of dollars, but like, and $1 million is even more. But when you get to this idea of billions and trillions and quadrillions, it's like really hard for us to wrap our brains around actually how big that is. Like, if you have $1 billion, that means you have $1 million 1,000 times. It's not just like a little bigger; it's 1,000 times bigger. Powers of 10. This is a really neat way to visualize sizes of things. Oops. Okay, symbolizing atoms. Oops. Okay. So, how are we going to symbolize atoms? So we have our, let's take something from the periodic table. I don't know. Let's say iron 56. Why did I choose iron 56? It's the most stable isotope in the entire universe. So what does this iron 56 mean? What does the 56 mean? Well, it means I can't pick an ink color. This 56 means it's the atomic what? Atomic mass, or we'll also hear it called mass number. And the mass number is equal to the sum of protons and neutrons in an individual atom. (26) is the atomic number. And the atomic number is the number of protons. Number of protons in an atom. And this defines what atom we have. Protons defines the atom. So any atom in the universe with 26 protons is iron. Any atom in the universe with 1 proton is hydrogen. Any atom with 2 is helium, etc., etc. Protons are the give the identity of an element. Sometimes you'll see this. You'll see it just with iron 56. Oh, sorry, I'm running over. I apologize. It's sometimes not shown because the symbol gives assumed atomic number. So if I give you the symbol, you just look at your periodic table and you can determine the number of protons. Okay, so, sorry, I ran over by 3 minutes. I apologize. If you're going to stay for X block, I'm here right now. Otherwise, I will see you Wednesday for quiz. Quiz. Homework is just to correct the problem set. Homework is just to correct the problem set. We'll get to this. We'll get to isotopes on Wednesday. This is room 454. There will be no lecture tomorrow. The next one will, you guys will get one on Wednesday, and another block will get. This is not 0. This is blank. Yeah. Yeah, that was really confusing. I apologize. How did they know they were positively charged? So yep.